Assalamu alaikum. In this lab, we will be implementing the deletion of a node from binary search tree. I have opened these two windows side by side so that we can discuss the theory of the process and we can see the implementation. So as we discussed already in the sessions that whenever there is a node to be deleted in a binary search tree, there are two fundamental pre-methods which are basically first you have to search for the node to be deleted, and then it follows the deletion operation follows after that. So whenever a node is found, after that we consider three cases for deletion, which we will be discussing in a while. So here this program is the same program that we have been coding since last few labs, which were the insertion and searching in a binary search tree, and then the traversal of a binary search tree, and now deletion. So in this method, in this program, I have declared this method delete, which accepts as argument a node and a value. So this value basically represents the key value of the node that you want to delete, and this method is returning a node type of reference. We will discuss later why it returns a node. Okay, so in this method, let's suppose we pass the root of the binary search tree, which is the actual root, and a value of the node which we want to delete. So what this method does, it basically initializes another temporary pointer current, and it initializes it with root, and it initializes another pointer parent, and it is also initialized with the root. So both current and parent are initially referencing the same node, which is referenced by the root pointer. Then there is a boolean variable is left child, which is initially assigned a value of false. We have already discussed this in the sessions, why we need this pointer, why we need this variable. It's needed because whenever a node to be deleted is found, you basically have to alter the left or right pointer, left child or right child pointer of the parent node. So we need to know that if we want to delete, if the node to be deleted is the left child of its parent or it's the right child. So to track this, we use this is left variable. So in a loop, what we do is current.data not equal to value until the value to be deleted is found. What we keep on doing is we initialize parent with current. So initially current was root, so parent becomes root again, and then we see that if the value is less than current.data, the value that we are searching is less than the data of the node which is pointed by current. So we move left. Current is equal to current.left moves the current pointer to the left. Since we move to the left, so it means that if the next node to which current will be pointing is the required node to be deleted, so it's the left child of its parent. Okay, else if this value is not less than current.data, it's greater, then we move the current pointer to the right, and we keep this is left child as false. So if current is equal to null, return current. After moving or promoting the current pointer, what we do is we check if it has become null, which means that the parent was a leaf node. Then we return current, which basically means that this is the node to be found. Okay, so current basically is representing the node that we are looking for, we are searching for, and it's the parent pointer, it represents the parent of this current pointer. So after you have reached here, it means that the node to be deleted is found. So once the node is found, what we do is we here, for example, when the node is found, you are going to delete. You need to consider the following three cases. The node that has to be deleted is a leaf node. If the node is a leaf node, which means that it does not have its left or right child, both its left and right child pointers are null, then we just print a message for our own ease that the leaf node deletion case. Now there can be a scenario where the binary search tree only has the root node, and the root node is a leaf node. It does not possess its right and left child are null. So in that case, if you want to delete this root node, then you just make this null. Root is equal to null, so binary search tree becomes empty. Else you check if this node which you have found to be deleted, if it's the left child of its parent, then you make its parent dot left is equal to null. Otherwise, if its left child is false, which means that you kept on moving towards the right of the root, so in that case you make the parent dot right is equal to null. So this is the easiest case of root deletion. So here also you can see the algorithm written in plain pseudocode or plain text. For example, in this case, if you want to delete 35, then you just have to make the right child of the 30 null. So current and parent both will be initialized with this 50, and then the value to be deleted is 35. So it will be compared with 50. It's less than 50, so current will move towards 30. Okay, and parent is equal to current. Current will make parent to 50, and current will be promoted to 30. Then after that, again this 35 is greater than 30, so parent will be made equal to current. Parent is 30 and current will be promoted to right, which is 35. Again here the value will be compared and it is equal, so loop will break, and you check if the current is not null, then you so it means the current is not null and the node is found which is to be deleted. So current is pointing to 35, parent is pointing to 30. Now here in the code you see that if current dot left and current dot right both are null, here is the condition, then you just make the parent dot right child null. So 30, the right child of the node 30 will be nullified, so it deletes 35. Okay, then there is the other case that node has one child. This case is also a bit more extensive but not that complicated. It actually has the same scenario as case 1, just a little bit of change. So here what we do is, if a node to be deleted has one child, then there are two scenarios. Of course there can be two scenarios, that the node to be deleted has either left child or it has right child, and the node to be deleted is either the left child of its parent or it's the right child of its parents. So we cover all these in just a simple if else statements. For example, here else if current dot left is equal to null. So the first condition was current dot left is equal to null and current dot right is equal to null. So if that condition is not met, it means we check here that if current dot left is equal to null, it means if this condition is true, it means that the left is null, left of current is null, and it only has a right child. So we just print a message, one right child deletion case. So in this case we check again if current is equal to root, the node that we want to delete. For example, here if you consider that 50 and it has 70 and it does not contain this left subtree, so in this case if we want to delete 50, So what we will do is we will make this 70 as the root. So 50 would be deleted and root would be pointed to this 70. So here we check if current is equal to root, then root is equal to current dot write. Else the node which we want to delete is not the root node. Then we check if is left child, when we were searching for the node to be deleted, if the is left child is true, it means that the node to be deleted has only right child and it is the left child of its parent. So in this case what we do is parent dot left is equal to current dot right. For example, consider here the case that okay, consider that there is 50 30, 50 has its children 30 and 70, okay, and then 30 has its left child, sorry, 30 does not contain 15, it only contains 35 as its right child. Okay, so what here we will do, if we want to delete 30, we would make the left child of 50 equal to right child of 30. That's what we would be doing to eliminate 30. Okay, so because we consider that 15 does not exist, only right child of 30 exists, which is 35. So we will just make the left child pointer of 50 equal to the right child pointer of 30. So that's what we are doing here in the code. Else if is left child, parent dot left is equal to current dot right, else parent dot right is equal to current dot right. Okay, because parent, if this node to be deleted is the right child of parent and it only has its right child, its own right child, then we make the right child pointer of parent equal to right child of current. Okay, then there is the case if the right child is null, if right child is null, so it means only left child exists for a node. For example, if we want to delete this 35 node, so in this case what we would do is we would make the right child of parent equal to left child of current. Okay, so for example, if in this tree 35 is to be deleted, then 30's right child should point to 31. So that's what we are doing here. Else if current dot right is equal to null, we print a message only left child deletion case. Then if this current if this root is the node which we want to delete, then we just make root is equal to current dot left. Otherwise, if this node to be deleted is the left child of its parent, we update the left pointer of parent, parent dot left is equal to current dot left. Otherwise, if this was the right child of its parent, then we make parent dot right is equal to current dot left. So in this way, this node deletion for a deletion case for a node with only one child is handled. Okay. Then the most complicated deletion case in a binary search tree is when a node to be deleted has both its left and right children. So in this case we have to first of all find the successor. We have already discussed it in theory. What is a successor node? Successor node is the immediate greater value of a node in the binary search tree. Okay, for example, if 30 is a node to be deleted, then the next greater value greater than 30, which if it exists anywhere in the binary search tree, it is the successor of this 30 node. But obviously it would exist in the right subtree of this 30 node. So we have to first find the in-order successor of the node to be deleted. Once it's found, then we have two scenarios based on the position of this successor node. Okay. For example, here it is written that once the in-order successor is found, there are two scenarios. Okay, before that, what is in-order successor? In-order successor is the next highest node, and to find it, you need to go to the right child of the deleted node, of the node to be deleted, and from there traverse the left subtree until null is encountered. Okay, for example, here in this tree, the successor of 30 is 35, which is the immediate right child of 30. Okay, but let's suppose I didn't give an example here, but it, for example, here. So in this case, not in this case, the successor for let's suppose 30 is 32, the next immediate value, the next greater value than 30, but this 32 is not the immediate right child of 30. So there are two scenarios for successor. Either it would be the immediate next right child of the node to be deleted, or it is the leftmost node of the right subtree of the node to be deleted. For example, in this case 30 is the node to be deleted and 32 is the leftmost child of the right subtree of 30. Okay, so so first we discuss when successor is the immediate right child of the node to be deleted. Basically, these 2 points, it shows here that if the in order successor is okay. Let's first discuss the method to find the successor of a node to be deleted. So we have defined here a method find successor. We pass it a node which is the node to be deleted. Okay, and it basically returns a node type of pointer, and this node would be pointing to the successor node. Okay, so what we initially do is we declare two node type pointers, successor and successor parent, and we initialize both of these pointers with the node to be deleted. For example, here let's suppose in this case, for example, here the node to be deleted is 30. Now we have to find the successor of 30 because 30 has two children. So when a node to be deleted has two children, we replace this node with its successor basically. So for that we need to find the successor of this node, and so this in the method we initialize both these pointers, successor and successor parent, with the node. So in this case, successor and successor parent, both these pointers would be referencing this node 30. Then we declare another pointer current and we initialize it with node dot right. So we initialize this pointer current with 35. It will be pointing to the node which has value 35. Now in this loop what we do is, while this current is not equal to null, so successor parent is equal to successor parent was initially pointing to 30 and now it is equal to successor, means that successor is also 30. Then successor is equal to current, so successor becomes this 35 because current was initialized with node dot right. So successor is equal to current makes the successor pointer to point to the node with value 35, and then we promote this current to current dot left. So current would be pointing to the left node of current, which in this case is null. Okay, so otherwise if it was not null it would be pointing to that, and then again successor parent would become successor parent would become 35 and successor would become would have become current, so because current was current in that case would be pointing to the left child of 35, and so on. This successor parent, successor and current, these three are basically would have been pointing to three different levels in the binary search tree. Okay, but for example in this case this is not the case. Current has become null once we moved the current to right, current dot left. Okay, so this loop would break. Now current is pointing, current is null, successor is current, which was 35, because before promoting the current to left we assigned the successor with current. So successor is 35 and successor parent was successor before updating successor to current. So successor at that case was 30, successor parent is also 30, then successor was promoted to current, which was 35, and then current was promoted to current dot left, which became null, and it mm, uh, certified the condition to exit this while loop. So now what we check is if successor is not equal to node dot right. Okay, now there are, as we discussed earlier too, and we also have here in pre-lab written here